can take data, we can transform data. A couple of weeks ago, I was talking to a friend, and his cousin was around, and the cousin was speaking to me on the phone and told me, "Tell me about what you do in 5 words. Tell me what you do as if I'm a 5-year-old." And I was like, how do I explain AI ML to a 5-year-old? So I said, okay, I make computers see, I make computers hear, and I make a computer understand you. So like, okay, that's good. All right, so let me quickly dive in. So what we'll be literally looking at, we'll be looking at selecting research papers for implementation. We'll be looking at effective research papers interpretation. We'll be looking at strategies for bringing research-based ML into product applications. And ML shows novel findings and developments and also shared insights into the latest happenings in the machine learning field. So you can find some of these papers will outline what has been achieved before, what is currently going on, and their novel findings of what they've discovered, right? And some of these papers are really, really important because majority of the new papers you see coming out that is talking about AI, talking about ML, right, are actually referencing old papers to buttress more of that. Yeah, so moving quickly because, like I mentioned, there are a lot of technical things at the back. So I just want to touch this overview as quickly as possible. When we talk about the relevance and impact of ML research papers in product applications, we'll talk about, I'm just going to outline about 6 points. They are more elaborate than this, but I'll start with these 6 points. So we're talking about the convey important breakthroughs. Like I mentioned before, some of the important breakthroughs in AI, like attention is all you need, AlexNet, diffusion, they all began from research papers, right? They all began from research papers. People pick up the previous work on it, expand it, find the loopholes, fix those loopholes, and push out novelty. So it comes, the research papers comes with unveiling important breakthroughs. They also share research work, right? And that was one of the big things that built the ML community globally. The availability of research work. Organizations go into spending a lot of time building, creating, and then they share those research papers publicly for people to read. And then when you read on it, you can use that to also expand your own work. And it literally reminds me of a time when I was working with audio content recognition. And the problem with this particular problem was that the audio data that was coming from production this time around, the sample rate changes dynamically. You could have something like 2205 to 410 to 4100 to 3600. So it was changing dynamically. And my head was cracking. The whole thing, you know that situation now. Your model.fit, model.predict is working fine. The moment you go to production like this, we start seeing cat as dog, leg as eye. You're like, what is going on? The boss now calls you and say, the customer is saying that their data is saying 100% when the ML has not even started. How? So at that point, what really saved me was this. So I went into RT and I started reading up on latest implementation. I went to some paper with codes and I started reading on how did people who have shared their work solve this problem of dynamic sample rates. And that was how I logged on the paper and I was able to cure that. So yeah, so they introduced novel practices. They help academia and industry implement in real time. You know, in this world of AI and ML, right? Academia is here, industry is here, right? They are two separate worlds entirely. If we bring academias to fill this room, the way we talk about AI and ML will be different, right? If we bring practitioners here, the discussion also will be different. So what papers help us do is bring a bridge between both sides and then allow us to iterate quickly and innovate. So build a technical portfolio. I mean, you go for an interview and you tell them, I read this paper and I implemented it. I don't want to know with that interviewer. He must do like this for you. It's definitely, right? So it builds your technical portfolio, and also advances technological growth in industries, right? The advent of ChatGPT, I mean, the amount of parameters it now covers with now, what's the latest ChatGPT now? 4? No, there's one recent one now that OpenAI just announced. Huh? 4V, exactly. 4V, right? 4V. And then everybody is just going crazy. Come and see LinkedIn. AGI is here. AGI is here. But how many of us believe AGI is here? How many of us believe AGI is here? Do we know AGI? I'm sure we know AGI, right? Okay, so AGI is artificial general intelligence. So we have artificial narrow intelligence, artificial super intelligence, and artificial general intelligence. Right? So artificial general intelligence is that point in AI where it is now aware, is now sentient. Do we know the story of Lambda? Google's Lambda? Okay, should I tell stories? Okay, so let me I will sneak this into 2 minutes of my time. So sometime in 2021, Google built their own advanced ChatGPT. Now, let me also clear something. The argument of OpenAI is better than Google. Please, what do they used to say? Trash it. Eh? There's one term they use. Please, perish the idea. Perish the idea. The idea that you are dragging OpenAI versus Google, please perish the idea. OpenAI was built on transformer architecture. Guess who introduced transformer architecture? Google. So please perish that your OpenAI is bigger than Google. Google bad, it's so nonsense. I've tested both of them. Please perish the idea. Google is just giving us bad because Google is not an open source organization. Google is majorly closed source with their AI, and that's what brought Elon Musk into this internal AI drama that is really riding on right now. So let me just sneak my 1 minute Lambda story. So in 2021, Google made Lambda, and Lambda was so powerful. I mean, so powerful that, and Google has this policy of cross-functional work. So Google brought an engineer from another department into the AI department and say, you are an AI engineer as well. Please help us evaluate this AI and document your report. Do you know what the engineer did? The senior engineer, after talking with Lambda and documenting his report, he went online and posted, Google's Lambda is now sentient. It is now aware, and the internet broke up. Everybody started shouting, Terminator is here. Terminator is here. They are killing us in the world, right? And Google got to know of it. And then they set up a panel to inquire on that Lambda. And then the inquiry came back that no, it's not sentient. It's just that it mimics some level of intelligence that would pass as something that is alive. And
This on the stage. Yeah, you can
so now, what brought me to this story? Lambda and GPT-4V, all of them actually bring about advanced technological growth in the industry. And that's the essence of research papers. When Google brought attention is all you need with transformer architecture and publish it, it broke the internet. And the organizations began to build. And then, very, very important, is it built on any of the community frameworks? Because majority of the people will explain how they arrived at the architecture. So was it built with Python, TensorFlow, or JAX? Right? And the reason why I'm citing this very importantly is you want to build what you can solve bugs for. Not that you are recreating a paper and you are finding the bug all over the internet. Because you may not even find the solution. And then, yeah, so these are some of very important paper sources. I'm sure majority of us are conversant with papers with code. And then we have AXV, we have SAN, and then we have neural IPS. Okay, so I won't spend so much time here. So how do you practically identify papers that really fit the approach or the problem you're trying to solve? One of them is you check what is benchmarked against. Some of these papers are benchmarked against other papers. For example, Llama 2 was benchmarked against GPT-3, benchmarked against Falcon. No, Falcon was benchmarked against Llama 2. Right, with GPT-3 and the other lesser LLMs. And then Falcon came up, Falcon benchmarked against Llama 2. So you find them using their novel approaches to benchmark others. And it's a very good way for you to deep dive in, because you check what was it benchmarked against, so I can know where was it coming from and where is it really heading to. And then ensure it aligns with the business goals and user needs, basically, before you start using that paper, because you want to really save yourself the time. And then that brings me to the end of that section with this very, very important citation. Most research papers, they introduce complex methodologies that really don't fit any product in reality. And it's a very big pitfall. One of my mentors, right, while I was working and building the audio content recognition engine, I brought a paper and I showed him and I said, I like this approach of these guys. I mean, look at the way they perform the audio augmentation, look at the way they transformed, using Fourier transformed, look at the way they created their spectrograms. I know, just look at the architecture, beautiful. He told me, don't waste your time. Look at their discussion. Look at it. They don't even know the outcome of their work. So majority of them will build, the papers do not really fit the products in reality. So you really want to watch out for that so you can save yourself from falling to that pitfall. And now let's look at how do we effectively implement these papers. How do you look at these papers and how do you implement them? So I'll be using this, so this is a very, very old, well, I wouldn't say really old. I would say the introduction was old, but the implementation is still used till date. Right, so this is AlexNet. Alex and the team introduced CNN rather, as an amazing implementation that ushered in the use of convolutional neural networks to solve many image problems. So I'll be using this to explain how to effectively implement them. So what do you really need to know if you're implementing research papers? The first you want to look at is what is the paper structure, what is the abstraction and the introduction from that paper, what is the related work, right? The discussion and the conclusion, the experimentation that was done, and finally you want to cite the reference. So these are actually the most important things you need to know to get you started. Research problem, pretty much close to what you have with normal research work, right? But this time the focus is on AI and ML. And you can find out that from the introduction, some very important things that was cited. You can see they said the size of our network made overfitting a significant problem. So you can see that they cited it there. So while you're working with it, you already know that they met overfitting as a problem. So you already have that at the back of your mind. By the way, ML engineers are amazing. What techniques, if you want to answer, just raise your hand, right? What techniques or technique can be used to combat overfitting in an ML model? Okay? Let me give you the mic.
My name is Samuel. One technique is getting more data for the model to generalize better on.
Okay, he said, get more data. Okay, somebody else wants to try. Sorry, you get to try.
Avoiding data leakage while training the model, so it doesn't cram some of the data and make predictions on.
Avoid data leakage. Sorry, just hold on.
You could also adjust the learning rate. Yeah.
Adjust the learning rate. Sorry, I will let you have some time.
Okay, another thing you can do is you can do oversampling or undersampling.
So he said you can use oversampling and undersampling. Okay, I would rather want to move that oversampling to where you have class imbalance for oversampling and undersampling. One way you can actively cure overfitting is dropouts, especially if you're working with ML models. Introduce dropouts. right? So that the model can adjust the number of neurons, especially in the dense layer. Okay, so let's move on. So you can also see mentioned that. Okay, I will explain that. Don't worry, I will explain that as we go. So you can also see they said our final network contains 5 convolutional neural networks, 3 fully connected layers, which is the dense layer, and their depth seems to be very important. So when you are reconstructing the paper, you see they mentioned very important. So when you are reconstructing, you know that the importance lies in the layers in your network, the CNN and the dense layer. So let's go on. Yeah, so then if you look at their discussion, right, like I mentioned, right, you start from the abstract and introduction, don't go to the architecture, don't go to data, jump to the discussion. You want to see what they really arrived at before you now come back to look at the architecture. And if you see, right, they mentioned that our result shows a large CNN is capable of achieving record-breaking results on highly challenging data sets using purely SL, just purely SL. I mean, this is really why these guys really broke the entire industry, right? Okay, so let me move on quickly. So then it comes to the experimentation section. And if you look at the experimentation section, they started mentioning about the architecture. They started by mentioning it contained 8 length layers, like they mentioned in the introduction. 8 length layers containing 5 CNN and 3 dense layers. And then they moved on to talk about how they contain the activation. They use ReLU, and then they mentioned that ReLU several times is faster than the conventional TAN. That's why they use ReLU. And then down here, they mentioned that these data sets had overfitting concern, and the effect they observed is different from accelerated abilities that feed the training, and then from what they reported using ReLU. So what I'm going to do is I have a link to this paper so you can just review, especially with the markers and all I did, so that I can really manage my time. I have just 30 minutes and I cannot really go deep, right? But at the end of the session, if you want to discuss any areas that you want me to go deeper, we can just hang out and hang around. Okay, so if you look at this, from all of these, I mean, mentioning from here down to using the CIFAR-10 data set, which is what they use. CIFAR-10 is available on sklearn. I think sklearn have it in their data set. I think also PyTorch has it in their data set as well. And how they achieve their trainings and down to their value activation. You find out that it's just basically this, right? The CNN layer is basically this. So this is my own rough note, right, of basically this. You find out that the first layer is an input dimension of an image with size 224 by 224. You know this is 3 channels, right? 3 channels. And then the output dimension is 11 by 11 for 3 channels. The kernel is 96 and the stride is 4. And then the second layer, they had the same thing, that is the output of becomes the input, and then the output dimension is a 5 by 5 or 48. The kernel is 256 and the stride is 1. So they did the same thing for all the CNN layers. And then finally for the 3 fully connected layers, they had 4,096 neurons. Okay, so in the next 5 to 10 minutes, I want to dwell here, right? I want to dwell here because this is what I will refer to as the crust or the crux, right, of my entire presentation today. So we're looking at strategies for bringing research-based ML into production. And I'd like to start with this, right? If you have been doing this for a long time, you get to realize that bringing ML into production, no be beans, right? It takes a lot. It takes a lot, right, to really bring ML into production. And some of the critical questions you find really is, what you find briefly is, how will the predictions be served, right? So you now have your model created from the paper, you already have the pre-processing from all that. Now you want to serve it. So you ask yourself, what stack will I need? How should the model experimentation design be done? And how will the ML meet the software system? Because majority of the time as AI ML engineers, right, there will always be an existing system that they've been using to serve the customers. They are bringing you on board to create the AI ML section for it to enhance productivity or to innovate. So you want to ask yourself, with my own AI ML, how will I bring it into the main system and serve the customers, right? Basically using their data to innovate. So we start from here, serving the model. How do you serve the model? So there are basically 4 ways you can serve the model depending on the business needs. We start with batch inference. One organization that uses batch inference right now is Netflix and AWS as well, right? So majority of the recommendation you see are not generated on the go. They will collect your data, understand your pattern for say 1 week, and then use that to generate predictions for you, store it in a DB, and when you come on the app, they just fetch it and they are showing you. So when you finish watching Anikulapo, they'll bring in a Jagun Jagun for you. I say, continue that war film way they watch. You like Yoruba film, Abi? Or yeah, continue and they go. So if you're like me and you finish watching Doctor Strange, they'll bring Avengers Endgame for you to continue watching. So that's where you have batch inference. Now for real-time inference, a good example for that is in healthcare, right? Where they are giving you predictions on the go, or they're serving you predictions on the go as a user. So you come into the platform, inference is generated right on the spot for you to enjoy. And then we have streaming, and then we have edge inference as well. So another way models are served is one-to-one or one-to-all. So what does this mean is that as an ML engineer rather, you're either serving your model as one model per client. One model per client. There are some clients that will bring in their own data to your organization. They have their own separate model. Or you are serving as one model to all. Say, for example, Car 45, right, or Netflix, right? So they serve one model to all. Right, so experimentation is at the heart. I mean, ML engineer, you are an experimentation person. You are experimenting 24/7. So you really cannot escape it as an ML engineer. So experimentation is at the heart. And what does it really look like? You have something like this. Your ML notebook should be detailed, descriptive, and sectionized, so that anybody that needs it can actually actively work with it. Yeah, I'm running. Okay, so I think I already explained this part. The repetitions. Okay, so that notebook I mentioned, you can actually see it here to look at how to structure your notebook, outline your notebook properly. So you can just find it here. You can take a screenshot if you want to. Yes, Jupyter Notebook. Okay, so I will move forward. Don't worry, the slide will be provided.
It's time for the next breakout session.
Okay, so basically to the end of it, let me just move. Let me stop. I'll stop my slide here. The other sections, you can actually comb them up from the slide even as they are provided. So when we talk about the two stack that you need, it's something like this, right? You have a two stack like this to cover all your ML deployment from feature store down to experimentation tracking. Let me just move down here as the last point. So in conclusion, basically, you find out that machine learning is very experimental, right? And even in production, you are always experimenting. Even in production, you're always experimenting as an ML engineer, start to the end, and that's it. So thank you so much, guys. I have to stop here.